Good afternoon, everyone. Thank you all for being here today for Dr. Faiz Makdisi's lecture. The lecture is part of the ERI's Treatment Family Visiting Professionals program, whose objective is to foster better understanding and communication between earthquake practitioners and academics. And Dr. Makdisi will also be available to chat with Berkeley graduate students after the lecture in this same Zoom room. So please do not leave if you are interested in learning more about his projects, career path, asking questions about your projects or similar. I would like to thank Megan for helping host this lecture and Connie for providing funds for lunch. Please make sure you do as Connie instructed in her email to receive the reimbursement. Now, it is my great honor to introduce Dr. Faiz Makdisi, a senior principal engineer of Gannett Fleming in Oakland. Dr. Makdisi received his Bachelor of Engineering from the American Uni of Beirut, Lebanon, and his master's and PhD in geotechnical engineering from UC Berkeley. He has over 39 years of specialized experience in geotechnical and earthquake engineering. Dr. Makdisi has been actively involved in studies of the seismic behavior of earth and rock fill dams and embankments. He developed and published with the late Professor Harry Bolton Seed widely used simplified procedures for estimating the dynamic response and permanent deformations in earth and rock fill dams. Recently, Dr. Makdisi has been involved in development of seismic design criteria, evaluation of seismic stability, and design of alternative remedial measures for more than 25 embankment dams. He is a recipient of the 1977 Norman Medal Award of the ASCE for the paper co-authored with Seed, Lee, and Idris on the analysis of the slides in the San Francisco dams during the 1971 San Fernando earthquake. Dr. Makdisi was a co-recipient of the U.S. Army Corps of Engineers, Chief of Engineers Design and Environmental Honor Award for 2002. He is currently serving as a member of the Board of Consultants for Oroville Dam Spillway Restoration Project and the Director's Safety Review Board for numerous dams for the California Department of Water Resources Division of Safety of Dams. Dr. Makdisi also served as a member of the Consulting Review Board for Conconally Dam for the U.S. Bureau of Reclamation. In 2017, Dr. Makdisi was awarded the Danny K. McCook Medal by Association of State Dam Safety Officials for his lasting contributions to dam safety. Please feel free to post any questions in the chat window, and I will read them at the end of the talk. Dr. Makdisi, please. Thank you.
Thank you, and I appreciate the introduction. I'm going to start the lecture by presenting the EERI's mission and their contributions to earthquake engineering risk reduction. And then I will continue on with the title of the lecture. I'm going to make sure here. Sharing my screen. You see my screen?
Yes.
Oh. Do you see my screen?
Yes.
Yes, we can see your screen.
Thank you. This will be a short presentation, basically on the function of the EERI. And it's, oops. All right. Just a short introduction. EERI has served a global earthquake engineering community. It is a nonprofit technical membership society and is dedicated to reducing earthquake risks. The mission of Earthquake Engineering Research Institute is to advance the science and practice of earthquake engineering, to improve understanding of the impacts of earthquakes, and to advocate for comprehensive and realistic remediation measures for reducing earthquake effects. Membership of the EER is multidisciplinary. It involves the geosciences, geologists, seismologists, engineers from structural, geotechnical, civil, transportation, and lifelines, architects and planners, social scientists, public officials, emergency managers, geoscience scientists, and economists and business analysts. And members of these disciplines involve either researchers or scientists, practicing professionals, professors, educators, government officials, building code regulators. It has a number of committees that addresses various disciplines. It promotes projects that would help turn research results into the practicing professionals. And it has a number of chapters, student chapters that at several universities throughout the United States and abroad. And the idea is to implement EERI's mission. What are the benefits for students? Well, this is one example. Maybe my lecture is not a very good benefit, but it's the Friedman Family Visiting Professionals Program, which is funded by EERI, and it allows for professionals like myself of various disciplines and experience to go visit universities every year, meet with the student chapters, meet with the professors, with graduate and undergraduate students, get an idea of what their research, ongoing research projects are, provide the experience that we have developed over the years in terms of our practices, and share it with the students and the professors. And for me, it's a great benefit. I've done this for the past maybe 15 or 18 years. The other benefit is involving the students in seismic design competitions in the annual meetings, providing for competition for student papers and providing awards for students, and providing fellowships for students, as well as visits to apply, especially graduate students that are doing research. They can get fellowships to go and improve their research topics and benefit from these. They also provide travel grants to EERI meetings. And there is an EERI internship program that helps students also participate in functions that would help them grow their experience with earthquake engineering. There is also online access to Earthquake Spectra, which is a very respected publication that has overall the results of, publishes the results of research that is related to earthquake engineering research, to public policy, to resilience and recovery from earthquakes, which is multidisciplinary. Well, after graduation, continuing membership and involvement in EER is very much encouraged. EERI membership demonstrates your commitment to reducing the earthquake risk. Student members get first year of your professional membership free and reduced rates for the next 4 years of professional membership. The last question usually they ask is, how did I get involved in EERI? Well, I started in 1975, before most of you were born, while I was a student at Berkeley. I became a member and attended my first EERI annual meeting in 1978. And I can tell you, over the past 40 years, as long as I'm able to attend the annual meeting and attend special meetings and learning from earthquake reconnaissance programs and so on, I have benefited immensely from my membership with EERI. One of the most exciting and rewarding experience has been my involvement in the Visiting Professionals Program. And over the years, I probably have attended meetings with the student chapter members at over maybe 10 or 20 universities throughout. Okay, let me just see what we do here. I'm going to turn over to the top topic of this lecture here. I'll make sure that we're doing it right now. Okay, I think as Zorana mentioned in her introduction, I had the honor and pleasure and the challenge and the excitement of serving on a very rewarding event that happened. I'm sure probably most of you have heard of the incident that occurred at the Oroville Spillway, Oroville Dam Spillway in 2017. At the outset of this presentation, I just want to acknowledge that most of what you're going to see in this presentation has been based on a presentation that was made by 3 members of that DWR program. Ted Craddock, who was the DWR is the Department of Water Resources, and he was the program manager for the recovery, they call it the Emergency Recovery Program of the spillways. Steve Varrigan was the Deputy Program Manager, and he was the GEI. Steve Varrigan used to be at the DWR as a Division of Safety of Dams before he retired and joined a consulting firm. Paul Schweiger is with Gannett Fleming. He's a colleague of mine, and he was member of the Consultant Review Board. The Consultant Review Board members are Kerry Cato, John Egbert, Eric Colgard, Paul Schweiger, and myself. And I want to acknowledge also the independent forensic team members who looked at the root causes of this failure and published a very well-studied report that provided significant improvements to the process of inspecting and checking out dams, and resulted in changes in regulatory agencies look at how dams are inspected and maintained. Presentation outline will just provide an orientation and general description of the Oroville Dam project, the 2017 spillway incident, the immediate recovery response, recovery of the main spillway, and recovery for the emergency spillway. Well, Oroville Dam is about 100 kilometers or 65 miles north of Sacramento, up in the Sierra Nevada mountains. It is one of the highest dams in the embankment dams in the United States, about 770 feet high. The main dam is shown in here, and also it impounds a 3.6 million acre-foot reservoir, provides water supply for about 25 million people, and also helps irrigate about 750,000 acres of irrigated farmland. This is the gated spillway, and you can see from this photo is at the time when the incident has occurred, and there was failure of a number of slabs of the spillway chute. You could see usually reference to it as an FCO, which is the flood control outlet structure. And the emergency spillway, which I think when the people designed this structure, they considered this emergency spillway may not have to operate throughout the life of the structure. The capacity of the gated spillway is about 296,000 cubic feet per second. The capacity of the emergency spillway is about 350,000 cubic feet per second. The gated spillway is about 3,000 feet. It shows it has different slopes. The first section that's down from the spillway gates is about 5%. And the second section, which is the sloped spillway, is about 25% slope. It's a 500-foot drop. And if there's enough flow at a speed, it could get velocity of fluid at close to about 170 feet per second. And this probably will show up next further on in this presentation of what's the impact of the velocity of flow on the pressures that could develop under the spillway. This plot shows the horizontal, the flow out of the spillway operations over the years, starting from 1969, 70, 2017. This is the outflow from the spillway in million acre feet. In 1969, it's about 2 million. In 1983 was about 2 million. 1997 was about 2 million. 2006, about a little bit, 1.5 million. And then in 2017, it was 5 million acre feet. Gives you an idea of what the level of flow out of that spillway compared to previous operations. This plot also shows what the discharges from the spillway in terms of cubic feet per second, not actual volumes like what we showed in the previous plot. During these years, in 1969, they had, actually 1970, they had about 110,000 cubic feet per second. 1986, they had 132,000 cubic feet per second. And these were usually years that they had significant rainfall and floods. And in 1997, they had about 130,000 CFS going down the spillway. And in 2017, this was just after the failure of the spillway, they had released about 100,000 CFS. 1986, as I mentioned, 137,000. 1997, 160,000 CFS. To put things in perspective, the spillway failed when the flow during the spillway chute was about 55,000 cubic feet per second. I think it's probably 55,000 cubic feet per second. This is the 1986 flood. It shows the flow down the spillway, and the flow was 137,000 cubic feet per second. In 1997, this shows the flow in the spillway chute with about 160,000 cubic feet per second. I'm showing the emergency spillway here to show that there are two components to the spillway. And let me just see if I can get a pointer here. The emergency spillway has two components. One of them is kind of an arc, like an arch concrete OG section, which is 980 feet. And then what they call a flat spillway section here, which is a very small weir. And the combined capacity of the emergency spillway is about 350,000 cubic feet per second. So let's look at what happened in 2017. This probably plot will show 2 or 3 times in the next slides. Flow between in January up to maybe earlier floods was about 30,000. And this was one of the wettest rains on record. By the time that we got the 1st of February, we had significant rainfall in January and December. And the plot that's shown in gray here is the inflow capacity in cubic feet per second. And you can see there's a significant rainstorm that was filling up and causing significant inflows. And when the predictions for these inflows were coming in, the flow through the spillway outlet gates were opened, and they released about 5,000 CFS through the spillway gates. The lower plot shows what the reservoir level is rising up very quickly due to the inflows from rainfalls. At the time of about the 7th of February, I'm going to go to the next one. At 10 a.m. on February 7, people were observing significant disturbance in the flow through the spillway. And the flow was about 52,500 CFS. And they noticed and saw some muddy water. You note that the estimated flow down the spillway for these 52,000 CFS was about 100 feet per second. The next thing that they noticed is when they saw this significant mud and unusual flow, they shut down the gates. And they noticed that part of the slabs of the spillway had been uplifted and significant erosion had occurred at that section. They inspected the spillway and noticed significant erosion. You could notice two things. One of them is even when there was no flow coming down the chute, there was significant flow coming from the under drains. These are outlets of under drains under the spillway slabs that are supposed to be relieving pore pressure and reducing uplift pressures under the spillway slabs. There was another observation that there are a number of trees very close to the spillway, and there was suspicion that maybe those tree roots have infiltrated the under drains and caused their plugging and resulted in uplift pressures. The gates, after looking at the damage, were reopened, and that's because there were significant projections for rainfall coming in and significant increases in the flow up to about 190,000 CFS into the reservoir. And the reservoir was just rising up, and people started getting concerned about potential getting up to the crest of the emergency spillway, which, as I said earlier, emergency spillways in these kinds of dam reservoirs and projects are not designed except through problems like what we're having right now. So they continued increasing the flow of the into the spillway for about 60,000 CFS. Continued flow into the reservoir. And if we look at the plot at the bottom of the slide, the reservoir got to the point where it started overtopping the crest of the spillway. The crest elevation of the spillway is elevation 901 feet, and the water started flowing over the crest of the spillway. Here's a shot of the flow that started after they opened up the gates to reduce the reservoir level and not allow it to go over the spillway or the emergency spillway. This 55,000 CFS flow started to erode significant scour holes in the foundation of the spillway at the location where the concrete slabs were uplifted and failed. In addition to that, you could see flow that's starting to flow over the emergency spillway. There was also concern about the dam has a significant hydropower plant at the toe of the dam that provided significant amount of power. And these are the transmission towers. And there was some concern about flow out of the emergency spillway and potential overtopping of the right walls of the gated spillway from eroding some of these towers. And there were emergency efforts to try to see if they can relocate those the transmission towers. as I mentioned, on February 12th, about 31 hours after the gates were opened, the reservoir peaked at elevation 902, which was about 1.5 feet over the crest of the emergency spillway. And the flow over the emergency spillway was not significant. It was about 12,500 cubic feet per second. If we compare that to the maximum design, which was 300,000 CFS, that's is not a significant amount. What was significant is the flow over the spillway, as low as it was, 12,500 CFS, 1.5 feet over the crest of the weir, started eroding the material downstream of the spillway. The spillway, the emergency spillway, is founded on very competent and fresh bedrock. But if people were watching what was going on, there was significant erosion downstream of the spillway. And you could see that certain areas here that started to erode, and this continued to erode. And you can see to the point here where the head cutting was backing up towards the emergency spillway concrete structure. And at that time, people were concerned about it getting in and underlying the emergency structure and failing that part of the structure and leading to probably about 20 or 30 feet of that reservoir going down the river and creating flooding. So that's when there was an evacuation order for 182,000 residents in the city of Oroville, until they were able to see if they can reduce down the reservoir level. What happened at that time is once the evacuation started, they decided to pick up the flow out of the spillway to about 100,000 CFS. And that started on the 12th of February. And this is what's a view of the water flowing down at 100,000 CFS through the spillway chute. Here's another view of it. And here's a third view. And that's what resulted from the flow through February 19. It eroded significant scour throughout the foundation of the spillway. The depth of this scour from this point here down to the bottom of the hole was about 140 feet. And the other result of this flow in here, between the flow that the erosion that went through the spillway here, it ended up in the river. It deposited about 1.5 million cubic yards in the river flow. The result of depositing these fractured and eroded rock had an impact on the power plant. There was concern that this will block the river flow and the water level in the downstream part of the powerhouse will flood the powerhouse and will put it out of commission and create quite a bit of damage and significant economic losses. What are the root causes and the contributing factors? There were 4 or 5 theories of what may have caused this failure. One of them was high groundwater levels have overwhelmed the drains and led to an uplift-induced failure. The other one was the slab drains were collapsed or plugged with tree roots and led to an uplift-induced failure. The third hypothesis was that foundation erosion and piping under the slabs could have resulted in failure of the slabs. The fourth one is that cavitation damage. Cavitation damage is the results of flow in concrete surfaces that are not very uniform will create cavitation, which is kind of like a collapse of vacuum that is caused by the flow of the waves and could erode the slab and will break it up. And the fifth one is the deterioration of concrete and joints led to hydraulic jacking of the excessive stagnation pressures. The first four hypotheses were not proved to be the cause. The fifth one is the deterioration of the concrete and the joints that led to hydraulic jacking from excessive stagnation pressures was considered a potential cause. Now, there are reasons for that. The slab for the spillway was designed to be a minimum of 15 inches thick with a reinforcement at the top reinforcement, with actually no water stops between the various slab sections. And there was a change in design that allowed the drains that are underlying the slab to be included within the slab, which at these drains, which are nearby the joints between each of these slabs, resulted in a thickness of the slab of less than 7 inches. And this change in design, which probably was not foreseen on its effects, resulted in significant cracking to the surface of the spillway. You could see when things were excavated to find out what the conditions are, this thickness here from the bottom of the drain to the top of the slab was less than 7 inches. Now, the other factor that contributed to the failure is the quality of the foundation bedrock that was supposed to be explored and excavated to moderately weathered rock or fresh rock. And there were changes that were made during construction that trying to probably expedite the completion of the project that allowed the pouring of the slab if you have at least half the area of the slab that is founded on good quality and unweathered rock fill, and the other part, 50%, is allowed to be not excavated. And that we'll show you how later on contributed to the potential for failure. Now, what they call these are herring cracks in here. The drains, because they have to drain down slope, so they were inclined at an angle so that they can drain down to the collectors, with very low thickness of concrete, cracked significantly. And this is a kind of a documentation of the repairs for the surfaces of the slab throughout the years, because of this change in the design that resulted in the concrete being cracked. These are examples of patching of these cracks over the years. And this is an example of the excavated thickness of the slab. In this case here, it's about 5.5 inches between the top of the drain pipe and the top of the slab. The other issue was the part of the flows through this photograph is after the failure. However, these drains were flowing at times even after the beginning of construction, they're not supposed to be flowing significantly, but this was a result of all these cracking in the surface of the concrete, and without also water stops between the joints between the slabs, there was a significant amount of surface flow that's coming down into the foundation. And it says, the title here says, immediately after construction, the concrete chute slab cracked above and along the under drain pipes, and high under drain flows were observed. This was also flow into February 2006, and all of these drains were flowing significantly. Now, the reason of why, what was the root cause of the potential failure of these slabs. These are examples of a spillway that has been displaced, and this is due to defects in a sense, or inconsistency between the slabs, openings in the slab, and offsets. And here's an example from Bureau of Reclamation based on a significant number of their spillway behaviors that they observed over the years. These are the two spillway slabs with some kind of an offset here, which is shown here between either 1/8 of an inch, 1/4 of an inch, 1/2 inch, or 3/4 of an inch. And this is a separation between the slabs. It needs only 1/8 of an inch, in this case here, and an offset maybe of less than an inch to create significant amount of uplift based on flows over the surface of the slab. If you noticed in the earlier slides that I noted, there were flows during maybe 50 or 60,000 CFS of flow in the spillway chute that could create somewhere between, let's assume we have 60 feet per second velocity, and assume an uplift, an offset in the slab of 3/4 of an inch, you could have close to 50 feet of waterhead pressure under the slab. And if you derive 50 by 60, this is about 3,000 pounds per square foot. That's a significant amount of uplift, combined with the potential for cracking causes the corrosion of the steel bars and failures of the reinforcing steel bars. This is what I covered earlier, the moderately weathered bedrock, that it was supposed to be excavated to moderately weathered or fresh bedrock before placing the foundation of the slab on the underlying foundation. But this issue during construction that said, well, if we have 50% of the area of the slab, of the concrete slab, has weathered material, but the other 50 was sitting on fresh or weathered or moderately weathered bedrock, we will allow the placement of that slab. That was a contributing factor. And you could see this photo of during construction. It shows significant amount of weathered soil as opposed to fresh or slightly weathered bedrock. The other part of it is, I'm going to mention this here. These are anchors. These anchors were designed to go 5 feet into fresh bedrock. That's the other example is this area where we had the failure was sitting on very highly weathered bedrock with a lot of shears in this section here. And this is where the failure started. I will show a photograph of the underside of this slab, which is upstream where the failure occurred. You notice the smoothness of the bottom of the slab, which means that it's sitting on uniform, either soil or some uniform weathered bedrock. And these are the depth of the half of a foot of this in the slab. So 4.5 feet is into highly weathered material. This anchor, which is supposed to be anchoring the slab to prevent uplift, was not providing its function. Well, as I mentioned, the independent forensic team provided the results of their investigations, and I'm quoting from them: the Oroville Dam spillway incident was caused by a long-term systemic failure to recognize and address inherent spillway design and construction weaknesses, poor bedrock quality, and the deteriorated surface spillway chute conditions. And here, I think that is surprising the process. Water injection through cracks and joints in the chute slab resulted in uplift forces beneath the slab that exceeded the uplift capacity and the structural strength of the slab at a location along the steep section of the chute. And that steep section allows for very high velocities. And with the offsets and cracks and irregularities in the surface flow, and with the absence of joints, stop plugs in the joints, resulted in uplift slab section exposed to underlying poor quality foundation rock at that location to unexpected severe erosion, resulting in removal of additional slab sections and additional erosion. Their conclusion, which everybody agrees with, there was no single root cause, nor was there a simple chain of events that led to the failure of the service spillway chute slab. The subsequent overtopping of the emergency spillway crest structure and the necessity of the evacuation order. The incident was caused by a complex interaction of relatively common physical, human, organizational, and industry factors, starting with the design of the project and continuing until the incident occurred. Well, what are the lessons learned in the industry? I'm going to quote from Pat Regan, who was a close friend of mine. Pat Regan was the chief dam safety engineer for Pacific Gas and Electric for a number of years. Then he left PG&E and joined FERC and was a regional engineer in the Portland district for a number of years. And then he joined the risk assessment group of FERC. FERC is the Federal Energy Regulatory Commission. He was in their group in Washington, DC, starting the risk assessments that kind of by now has resulted in providing risk assessments for dam safety. He analyzed the failure of more than 1,100 dams. And approximately half of these failures occurred after 50 years of operation. And his observation was an extended period of apparently successful operation does not indicate an equally successful operation in the future. The other conclusion that the forensic team came up with is that physical inspections, while necessary, are not sufficient to identify risks and manage safety. At Oroville Dam, more frequent physical inspections would not likely have uncovered the issues which led to the spillway incident. Comprehensive periodic reviews of original design and construction, taking into account comparisons with the current state of practice, are needed for all components of the dam projects. You know, there's a tendency with saying this has been designed in 1972 with current standards at the time that were adequate for designs at that time. But the industry has learned significantly in the past 50 years, and significant practices have changed. So it is behooving on inspections right now and for inspectors. And I served as an independent consultant for FERC inspections for the past 18 years, is not to accept what was designed at the time, but check it out and compare with what we do currently in practice. And if there are deficiencies in when the dam was designed or that component was designed from what is currently accepted in practice, that needs to be assessed and if need be retrofitted. Okay, having looked at the incident and the lessons learned, it was a challenge to get this thing operational back. The restoring of the spillway capacity was significant to do that before the next flood season. And that created some challenges. The guidelines or the goals for the first year of construction was to restore the capacity of the spillway, to armor the existing spillway where it's not restored, and design. The design period was between March and June. To mobilize in April because they were still doing design, but they advertised for construction and selected a contractor to start constructing in June. And to finish the first section of the spillway recovery project by November 1st. So what were the milestones? There was a spillway management organized. This was on the 14th of February. The recovery framework was adopted on the 23rd of February. The first meeting of the Board of Consultants was on the 1st of March. And this Board of Consultants was requested by the California Department of Water Resources Division of Safety of Dams and the Federal Energy Regulatory Commission. They organized spillway team leads on the 6th of March. They did alternatives analyses by the 17th of March. They advertised for a spillway contract by the end of March. They awarded the spillway contract to Kiewit Pacific by the 20th of April, and they finalized the plans and specifications by the 21st June. Well, what the key design considerations were to fill up those scour holes that were, dug or eroded to a depth of about 140 feet. And at the same time, also they contracted with a research university to do hydraulic modeling to find out what are the better approaches of designing the fix. And that was kind of an interesting also exercise. But the idea was to do this, to restore the spillways over 2 construction seasons. The first construction season, which starts in June, is to reconstruct the downstream section of the spillway chute and the middle section of the spillway chute. This main section here is the area where they have the significant erosion, is to backfill it with reinforced roller compacted concrete. This is a profile of the spillway here, to fill this one up here all the way to the surface, and to build what they call interim spillway chute here over this RCC section. And the upper section here is to try to clean any concrete cracks, fix it as better as they can, and delay it till the next construction season. The next construction season was to replace these interim chute walls and rebuild the section here and the section on the upstream area. This is what it looked like in February 19, 2017. That's the area that was refilled with RCC during the first summer construction season. And these were the 2 reconstructed sections, the lower section of the spillway chute and the middle section of the spillway chute. This area shows what was demolished of the old spillway section at the lower part, and what the area that has been still excavated down to bedrock in the scour holes. And just to compare with what I showed of the quality of the soil and weathered rock in the old spillway construction, they have been going down to very fresh rock right now, and even vacuuming and pressure washing and getting down to fresh rock. And then they will fill it up with concrete, and then they place the slab on it. Here's an example of how clean they're getting down to fresh rock compared to what they did during construction in 1972. This is a profile of what the new slab would look like. This is all concrete that is, they call it leveling concrete, that comes in. This is the drain that's under the slab. The slab is 2 feet, 30 inches instead of 7 inches here. With double reinforcement, water stops in here, and with anchors that go down 15 to 25 feet into fresh rock. And here's what existed in the old section of this slab. 1 foot 3 inches was about 15 inches, minus the drain, which leaves about 7 inches of thickness. And here's the drain below it. This is the leveling concrete. And this is all the weathered and broken up rock that was underlying the slab. And this is the depth of the anchor that was supposed to prevent uplift in the old slab. This is a three-dimensional model of what the new slab and the retaining walls. As I mentioned, the new anchors go down 15 to 25 feet into fresh rock. These are the drains, and these are the water stops between the slabs. This is the interim RCC, because they built up these 140 or so scour holes, and to build on top of that would take quite a bit of time to reconstruct and build new concrete slabs and walls. So they decided to build these interim retaining walls from RCC. And these will serve the first construction season. Here's an example of where the RCC is coming up to grade, and they're constructing the retaining walls from roller compacted concrete. Here's a view of what the reinforcement for the new slabs. These are the water stops, the upper and lower reinforcing slab, steel. And this is the activity during construction. This was the middle section that was being constructed in the first summer season. And there were 700 workers working 24 hours a day in 3 shifts, 7 days a week. Here's an example of what the retaining walls for the new slab, for the new spillway section. And this is the kind of progress during the first summer. Here's in May, where the scour holes are still open. In June 30th, they're starting cleaning up. In June 30th, they're starting putting the RCC sections in here and raising up. They've started, they demolished all the existing old concrete spillway chute, and they've started putting the slabs in here. The same thing with the upper portion. Continues on. Here's where the RCC is coming up to the surface and filling it up. The RCC is completed here, section, with the walls, the interim walls. This is the new structural concrete slab down at the bottom section, and this is the upper section. That's November 1st, 2017 is when they completed that section, the first construction season. Okay, now the next description is what was done at the spillway section. As I mentioned, here's the OG section, and the deepest part of this is just like a concrete gravity dam. The deepest part of this section here is about maybe 80 feet. And this section here is what we call, they're calling it the flat pier section. If you notice, there was significant erosion in this area throughout. So this area was excavated down to fresh to moderately weathered bedrock to make sure that if this emergency spillway will operate again, that this would be all filled with an RCC. There will be a secant pile cutoff wall here to prevent any erosion downstream of this from backing up and cutting up into this area here. This was an RCC apron that was filled from the secant pile wall all the way to the toe of the OG structure of the emergency spillway. And here's a profile of it. This is the section I was showing you that has the maximum height of about 90 feet. This, what they call this Rcc apron, after excavating to fresh to moderately weathered bedrock. This is the cutoff wall, that will be excavated all the way down to somewhere between 35 and 65 feet. And as I will show you later, they even went down to 95 feet in the weathered bedrock area. If you notice, they've analyzed the seismic stability of this structure here, and they found out that it needs buttressing. So there is a buttress for this structure here as part of the section with reinforced rural compacted concrete buttressing. This is a profile of the secant pile wall. If you notice, the deepest part in the weathered area, which is in this section here, went down to 90 feet. This is kind of as a training pile for guiding the drilling of these secant pile walls. And because of the difficult drilling conditions in bedrock here, this process was getting a little bit slow. So the contractor has to bring in 5 drill rigs and continuously work. The idea was to create these cutoff walls. These are the secant piles, and they overlap, but to reduce, to make sure that whatever groundwater that is under the slab, under the apron, will still drain. These were panels, and there were spaces that left open between these panels to provide for seepage to flow between these panels. That's what the spillway, the erosion, the emergency spillway looked like after it was completed. In July 4th, 2018, they started on the second part of the construction, which meant that they had to go up and demolish the upstream section that wasn't reconstructed. They had to go in and demolish all the interim retaining walls and clean up the RCC foundation. And that's what it looked like in November 18th, 2018. They did some also retrofit to the energy dissipators down at the bottom of the spillway. And November 2018, this project was completed. And here's a photograph of all the people that will work on this project. And I'm open to questions. I think I finished in 1 hour. Just as a note, we had monthly meetings as the Board of Consultants. We'll go and spend 2 days. We will have presentations made to us by the project team. We will be given a set of questions at the end of the first day after we've been given all the presentations. We will spend the next day and before they started construction or do anything, we will spend the next day in the morning going through the presentations, and we had to respond. And after lunch, we will have to write our report in the morning, and after lunch, we'll do a proofreading of our report after lunch. So mostly it was 2 days. If there was a significant amount of construction that is going on, we would go and spill to a third day. It was the most challenging, rewarding experience that I, enjoyed, and at times it was kind of challenging. And but it's the process that went through for these 2 years was an amazing achievement.
Thank you, Dr. Makdisi. That was excellent presentation, amazing project, and the scale is just amazing of the project. So please, I haven't seen any questions in the chat, so please feel free to unmute yourselves and ask questions. Okay, Sejong Che is asking, Sejong Che, would you like to unmute yourself and ask the question itself, or would you like me to read it? So, is interested in how you inspect failing buildings safely.
Failing
Buildings safely. How to inspect for failing buildings safely.
I'm not sure I understand the question.
Sejong, I'm sorry if I'm not pronouncing the name correctly. Would you please like to ask the question yourself?
If I understood what you're asking, I would say I will hire a structural engineer. Yeah, I'm not. If the question is, how do you decide if building is failing first? If it's failing, probably don't go in there and inspect it. I'm not sure exactly what the question, what you're looking for.
Okay.
I have a question. I'm Abdel from Virginia Tech, and I want to thank you for the presentation. Thank you very much. I just wanted to ask, so you showed the project from multi-different areas, and in practice, sometimes it could be easy to be blindsided into one particular direction. And I was wondering, how is the industry moving forward into integrating all these different disciplines and different aspects of such a large scale project, which is part of like the big data, and how is industry moving towards that direction?
Well, I think the lessons learned in here, and if you noticed early on in these inspections, this Oroville Dam is a 770-foot high dam. People concentrated more on the dam, and maybe they haven't paid enough attention to other critical aspects. These days, the kind of the risk-informed decision-making or inspection is you look at all components of the project and make sure that you understand that these components are designed to serve their function. The process starts with a potential failure modes analyses that looks at every significant component of the project and looks at what are modes of failure or what are defects that would start and continue and progress and result in this case for embankment dams or reservoirs, to uncontrolled release. First, that was the focus in earlier inspections. Recently, it has migrated to looking at every single component that is designed to serve a function. And if the failure of that component to perform as it is designed, and if that failure leads to either to economic losses, disruptions, environmental concerns, not necessarily releasing the reservoir, this will be considered as a credible potential failure mode, and it needs to be addressed. Did I answer your question?
Yes, thank you very much.
You're welcome.
Can I ask a quick question about the monitoring? You had a comment that that they kind of assessed that monitoring of the structure wasn't going to be helpful for kind of detecting the failure. And could you elaborate on what kind of monitoring was done, and maybe if there was any type of monitoring that would have been effective?
Modeling, you mean?
Monitoring, like monitoring.
Monitoring.
Yeah.
Yeah, I think they were talking about inspections and monitoring, and they were doing a lot of that. And they were doing fixing of all these cracks over the years, and some of the repairs had deteriorated again, and they were fixed again. But nobody went back and said, okay, let's look at why do we have these persistent cracks, and get back to the design and see that, well, we're looking at a slab that was designed to be 15 inches thick with single reinforcement. This was the practice at the time. But why are we getting all this cracking and the deterioration of the concrete at these? And if you notice in the photograph that I showed, these herringbone, they call them herringbone cracking. These were following the drains, the direction of the drains. And that's where they had the 7-inch thickness of the slab that was cracked. That cracking allowed for corrosion of this reinforcing steel and failure of this reinforcing steel, and the lack of water stops between the slab joints allowed for water to flow in between, and for a failure of these stops, of the caulking of these stops, will create more than 1/8 of an inch separation. And if you have any offset from the plots that I showed from the Bureau of Reclamation's experience in their spillways, you don't need significant velocity flow over this offset and the separation between the slabs to create significant, they call them uplift pressures that would lift the slab and erode below it. The combination of the weathered material below the slabs, the fact that these anchors, which are 5 feet deep into very highly weathered bedrock, or sometimes soil that was left in place, and the cracking of the concrete, and the lack of water stops, created these significant uplift pressures for velocities of the range of about 50 or 60, or maybe even there were flows about 100 CFS. Sorry, 100 feet per second. You could get about 50 or 60 feet of water head under that slab. Multiply that by 62.4, you get about 3,000 pounds per square foot. Uplifting forces. And where it failed, the first slab that was uplifted is that zone of deteriorated weathered rock and shear zone under that spillway.
Thank you. So you're saying kind of a reassessment of the design was kind of needed in terms of monitoring, after monitoring, I guess. Yeah.
Right. I don't think somebody went back and said, well, why are we watching all of these cracks and we'll keep fixing them and then they crack again? To go back and look at the design and go back and maybe review the foundation. There was a very detailed mapping of the excavation of the foundation for that chute. And you could see areas of weathered rock that was in there. But somehow, I don't think during construction they decided to go and follow the specifications that says you go and excavate with pieces of equipment till you get refusal. And if you notice that under the slab photo of that lifted slab that was still standing there, it was smooth. It was smooth, it means it was sitting on a uniform surface soil that is soil and rock maybe. And those anchors were just floating.